All right, well, this is our penultimate session. There's that SAT, yeah, there's that SAT word, which means next to last. And I don't actually think that we'll have a recording for the last session because I'm not sure what we're going to do tomorrow. I don't think there's anything left to do. But let me just tell you a little bit about what's going to be on the final. Now, here's the thing about the final. It's going to be cumulative, but I obviously want you to concentrate on the stuff from this last material. So here's what we're going to do. It would be asking, I think, way too much for you to go back and review every little nook and cranny of all those other paradigms and have all that stuff rattling around in your head. So let's just say this. I'll make a deal with you. I will say that there will be one review question on the functional paradigm, one review on the logic paradigm, and those questions will simply be from the exercises. All right? So if you just want a quick review, you can just, if you want to review that material, all you need to do is just go through the assignment, the assignments, and just review all the homeworks that you did. Okay? So I'll just pick one. I'll just pick one from each one of those. And that's all. And then every other question will be from the concurrency paradigm. All right? So I think that should narrow down what you have to, look at when you review. And then other than that, I think there's nothing else that I need to tell you about the final, because most of it will be on this concurrency stuff. Maybe if you have questions, yeah. Mm-hmm.
How many theory questions will it be compared to coding?
Oh, the question was how many questions on theory versus coding. I don't know, but there will definitely be both.
Okay.
Yeah, there will definitely be both, and I will ask you. I will ask you. I'll tell you what. Let's say this in terms of the coding. Java is just so, there's just so much, miscellaneous irrelevant stuff. Why don't we just say there won't be any Java code? All right? So so let's just have the coding either be from like his theory language or from C++. Okay, so let's say no Java code. Because Java, you got to do the try. Oh, except for one thing, I did tell you that there is going to be one question on there about Java. I will give you the code for, what was the example number from Sestov? The try catch finally.
Yeah.
Maybe we could do that tomorrow. Maybe we could. That might be a nice review to go through that. We could do the demo. I mean, we could just go through it together. Right? That would be a nice. Yeah, I think that would be a good way to spend some time. Figure, see how that works.
On the exam, we would just have to do a prediction.
Yeah, I would predict. I wouldn't ask you for every single one of them. I'd give you a 3-digit number and say, now what's the output of this try catch finally? Example from Sestov. And I will obviously give you that code. Yeah, so let's do that. Or we might even be able to, if you want to, we could do that today, because I don't think this is going to take very long.
So for the coding, to reiterate, C++ with like the pseudo code that's in the book?
Yes, C++ and or the code that's in the book. Right.
Are you going to give us the code in the book if we have to code up one of the...
I might give you some code on this one. On this one, I might give you some code to code up a problem that you haven't seen before.
Okay.
Sorry, I might give you a problem to code up the solution to something that you haven't seen before.
But it's still translating?
No,
Okay.
not necessarily just translating.
So we're going to have to write...
I might ask you to write an algorithm to solve a problem that you haven't seen before.
But write it in C minus or write it in?
Oh, in C minus
Okay,
minus.
so we won't be writing the pseudocode.
Um,
We won't be.
Yeah, you know what? I'm really loosey. I mean, write it in C minus minus, but I'm not overly concerned with syntax.
Okay.
You see what I'm saying? I'm kind of loose. I mean, I'd rather, you don't have to worry if you don't get every brace. I mean, if you indent correctly and you don't put the brace, yeah, I'm not concerned about that.
One of those weird things that are, is it the plus plus that's not in C minus minus or the something like that?
C minus minus doesn't have a bool, type bool. But you know, you can go ahead and assume that it has type, it should have type bool. Go ahead and assume that it does on the test. I mean, I don't care.
It doesn't have plus gets either, though, right?
Say it
It
again?
doesn't have plus gets.
Does it have plus gets?
I don't think so. I tried to.
You tried it?
I thought so.
Did you try it and it did?
That's what's in my memory, but that was from a couple weeks ago, so it could be wrong.
Yeah, I don't know the answer to that
I tried to use it
question.
on my last one and it said it wouldn't work.
Oh, you plus gets wouldn't work? Oh, well, maybe. Yeah, I'd have to do an experiment, but for example, if that's the case, if it doesn't have plus gets and you use plus gets, no big deal. That's not a problem. That's the logic of the concurrency that counts. Well, but with some code. I mean, you know, if the code is logically correct. Anyway. Okay, are we good? Actually, I think we'll have time today to go through the Sestoft example. All right, now here's what I would like to finish up with. Now, and this material is not going to be on the exam. But I think this is a very interesting, and for me, it's a really exciting recent development. Now, and for those of you who took data structures last year, we have transitioned and in the data structures course are now requiring compiling with the C++ 11 standard. So 11 stands for 2011, and that's when the standard was finalized, and it always takes a little time for the compilers to become compliant. And so now, it's been 2 years since then, and so now the compilers are pretty, they're pretty compliant. They're all usable. And so now that we're in C++ 11, well now, and here's something interesting, you guys. Our very first paradigm in this class was the functional paradigm. Guess what? In C++ 11, they have added lambda functions. Yeah. They have added, because there are situations where when they arise, they are really useful. And in fact, in the data structures class this semester now, we use the lambda function in the B tree. I don't know if you guys remember from last year. Those of you who took data structures last year, remember the B tree? We have a new implementation of the B tree that uses that lambda function feature of C++ 11. We have a new implementation of it, of the B tree. And so that's been really nice. But, so that's one thing where C++ 11 is relevant to this paradigms class. But the other really big thing is that with C++ 11, they have finally added now concurrency. Now, Java had concurrency from the beginning. And with C and C++, up until the C++ 11 standard, the way you did concurrency was with a library. But there has been growing recognition that to do concurrency right, you cannot just rely on a library. The language itself needs to support concurrency. And up until 2 years ago, C++ did not do that. Instead, you accessed concurrency through a library. And the typical library that you used, and we never did learn this model, but they were called p-threads. Has anyone here ever heard of p-threads? Have you heard of p-threads?
We use it in operating system.
Oh, an operating system. Oh, yeah, you learn p-threads in operating system. Oh, yeah, that's good. Yeah. So, but you know, it's a pretty low-level thing, and the concept, it's not conducive for teaching the concepts because, you know, like I say, there is growing recognition that to do concurrency right, concurrency has to be in the language. Now here's another thing you guys should know. There is a language out there that did it really, really well. And it's called Ada. Have I mentioned Ada in here before, or have you heard of it? In fact, I think our author has some Ada code. I think there's Ada in our textbook. In fact, I'm sure there is. He does. But see, what Ada, the general approach that Ada took was a slightly different one. Instead of shared memory, it was message passing. And so there's another whole set of primitives. Unfortunately, this is not a course just on concurrency. If it were, we would get into that other, there's another whole way to do concurrency, which is different from these shared variables, okay? And Ada, the concurrency is built into the language, and it's very robust. I mean, these guys, the guys who designed this language, I mean, the way this language has evolved, it's technically, it's very sound. It's really good. And there was, it has an interesting history. What happened was the Defense Department in the United States was contracting all this work out to all these aerospace companies, and they were using all these different kinds of languages, and the Defense Department said, look, this is just getting unmanageable. We need a single language and then we're going to mandate that everybody uses this one language. So they put out, and I was around, I remember the process well. So they put out bids, and there was a competition, and different groups proposed different programming languages. This was a programming language that was actually designed by, it was a competition. And then the Department of Defense picked this one language that was designed by an individual. Iqbal was his name. And Ada, the name Ada comes from Ada Lovelace. Do you know who Ada Lovelace is? She's credited with being the world's first programmer. She worked with Charles Babbage. Do you know who Charles Babbage was? He was like in I think it was the late 1800s. And Babbage, he designed this mechanical analytical engine, I think is what he called it. And it had gears and wheels and stuff. And the concept was ahead of its time. You could program it mechanically. And so she is credited with being the world's first programmer. But unfortunately, the machine was ahead of its time, and the tolerances, they couldn't build it a reliable version of it, And so it kind of fell by the wayside until electronic computers came on the scene. So it's named after Ada Lovelace. You can Google that. All that information's online.
That's a really long time.
Actually, Google it.
Yeah.
Say what's the time frame on that?
Well, so that she lived like the 1800s.
1800s, yeah. So
1815 to
1850.
1852.
Oh, I said late 1800s. It's mid to early. Yeah, mid 1800s. And does it mention Charles Babbage?
They met at a party in
They met
1833.
at a party in 1833. Yeah, and she was a mathematician, I think, or he was. And yeah, and so, but unfortunately, 1800s. It's an interesting history, and there's lots of pictures of Ada Lovelace. And Byron, wasn't she? How was she related? She was what does it say? Was she married to Lord Byron?
It says,
I kind of forgot my history here.
sorry, I'm like reading it.
Huh?
Sorry, I'm like still.
Yeah.
Makes sense what it's saying, but,
Oh, okay. Well, some interesting history
it
there.
says she was the first to express the potential for computers outside of mathematics.
Okay.
She was a child of Lord Byron.
Child of Lord Byron. Yes, that's what it was. So anyway, so that's interesting. And this language, the reason this language is interesting is because they had concurrency in from the beginning. And in fact, I used to teach Ada here, and then, you know, because it was a good language. It still is. In fact, it's still widely used. It's kind of like unknown, but widely used for especially in the commercial aircraft. You know, the controllers for airplanes, is a lot of that stuff's still written in Ada. And it's not a dead language. It continues to evolve. They continue to do put object orientation in it and all that kind of stuff. So it's a good solid language. But anyway, I'm really excited about the C++ 11 because of this realization that concurrency has to be built into the language in order for it to be done right, and the fact that it's coming kind of late. Because, you know, Java has had concurrency for a long time. We've had lots of experience with Ada. It looks to me like they did a really good job of putting concurrency into C++. And so what I want to do is I want to show you some of the features of that.
Okay, so we're doing a little time jump here to 2021, at which point we have abandoned the old C++ language that we were using before when this recording was begun, to C++ 17. And at the end of the previous recording, we had shown ReadersWriterC, which is very simple to program, because the designers of C++ 17 have built in a sophisticated algorithm called the tarekhoff algorithm into the language, and so we saw ReadersWriterC in the previous recording. And the thing about it is that when a lock is allocated on the runtime stack, its constructor locks the mutex, but you can't actually see the code that the constructor executes when it locks the mutex, so it's not visible in the code. And similarly, when a lock is deallocated, when a function terminates, its destructor unlocks the mutex. But here again, the unlock operation is not visible in the code. So that's why the code in ReadersWriterC is so easy to write. But what we want to do here is we want to explore the actual algorithm that goes on behind locking and unlocking shared and exclusive use mutexes. So what we're going to do now is look at ReadersWriterC. Now what we have done here is that we have actually programmed the solution to the ReadersWriterC program without using the shared mutex. So even though that solution is supplied to us by the shared mutex feature of C++ 17, what we're going to do now is take a look at an implementation of the ReadersWriterC that the shared mutex actually does behind the scenes. So we have a solution here of the ReadersWriterC that shows the algorithm used by the shared lock. Now I've taken a little bit of liberty to change the terminology from C++ 17 to the terminology that's used in our great textbook by Benari. So in this following code that we're going to look at, start read, what we call start read in ReadersWriterC, corresponds to lock shared in C++ 17. And end read corresponds to unlock shared. And so you can see the similarity there whenever we do a start read and an end read to the lock shared and unlock shared. Because it's shared, that means several readers can be in the database at the same time. And then our start write corresponds to lock, and our end write corresponds to unlock. So that's for exclusive access as usual, without using the shared feature. So let's take a look here at the tarekhoff algorithm that C++ 17 uses to implement the solution to the ReadersWriterC problem. Now, as with the horse semantics solution, there are two condition variables, but this time the condition variables are named gate1 and gate2, and they operate differently from the way they did, or from the way they do in the horse semantics solution to the ReadersWriterC problem. And in addition to these two condition variables, gate1 and gate2, we're going to have one int variable named readers that's going to keep track of the number of readers inside gate 1. And then we're also going to keep track of whether or not a writer is inside gate 1 or gate 2, and that's going to be a Boolean. So we're going to have one int to count the number of readers and one bool to indicate whether a writer is inside gate 1 or gate 2. Now there are 4 rules that are explained on the next slide, but before we take a look at those 4 rules, I think it'd be better for us to take a look at a little visual that I've developed here on this next slide. So here's a visual picture of the operation. Now, so let's analyze this figure for a minute before we get to the rules. You see there are a number of readers and writers that are waiting outside gate 1. And these readers and writers can, they both go through the same gate. They both go through gate 1. And let's suppose that a number of readers go inside gate 1. Well, if you can have like 3 or 4 or as many readers as you want inside gate 1. And while they are inside gate 1, they actually have access to the database to read it. And so readers can enter gate 1 and exit gate 1. And when they're inside gate 1, oh, and by the way, notice that the reader's exit is to the right. So a reader goes inside gate 1 and a reader exits without going through gate 2. Gate 2 is only for the writer. Now what happens is, if there are a bunch of readers inside gate 1 and they're reading the database, and then if the first writer to enter gate 1, once that writer enters gate 1, both readers and writers are blocked on gate 1. And furthermore, if that writer tries to go into gate 2, that writer is blocked until the number of readers inside gate 1 drops to 0. So what happens is, we'll do a little trace of this in a few slides here in a minute. But what happens then is once the readers exit and there's only one writer inside gate 2, that's when the writer can go through gate 2 and into that second room. And as long as the writer is inside gate 1 or inside gate 2, whether he's in the first room or the second room, as long as a writer exists in either of those two places, all the readers and all the writers are blocked on gate 1. Then what will happen is, eventually the writer will finish his writing and he will update the database, and then once the writer exits, then we will return to the initial state, and the readers and writers can both start getting in. The readers and a writer can start getting inside gate 1. So that's the visual. So remember this visual. Gate 1 for both readers and writers. The readers exit gate 1. They never go through gate 2. Once a writer is inside gate 1, once the writer is inside gate 1 or gate 2, readers and writers are blocked on gate 1. If a writer tries to go through gate 2, he cannot until the number of readers goes to 0. So those rules are all summarized in this following slide. So let's take a look here. Okay, so here are the rules. When a reader enters gate 1, it has read access. However, a writer must first enter gate 1 and then gate 2 to have write access. So remember, that writer has to go to that second room. Rule number 2. There can be any number of readers and at most one writer inside gate 1. And furthermore, there cannot be any writers inside gate 2. You remember that little exit room to the right on that first room, that's where the readers exit. So there cannot be any readers inside gate 2. Third rule. No one can enter gate 1 if a writer is inside gate 1 or gate 2. If a reader or writer tries to enter, it is blocked on gate 1. So that keeps both readers and writers outside of gate 1 as long as there is one writer inside gate 1 or gate 2. And the last rule is, a writer can only enter gate 2 when the number of readers inside gate 1 drops to 0. If it tries to enter gate 2 when there are readers inside gate 1, it is blocked on gate 2. Okay, so now those are the rules, and I have a little visual here to show the progression of what happens with this algorithm. It's actually, I think it's easier to understand than the solution to the readers-writers problem with using the horse semantics that we looked at before. Okay, so let's run through the sequence. So here is the initial state. We have a number of readers and writers outside trying to get inside gate 1. Okay, so first what happens is, some readers enter gate 1. So readers are going inside gate 1, they're reading, there can be more than one reader at a time, they're entering through gate 1, they're exiting through that reader's exit on the right of the top room. Eventually what will happen is a writer will get inside gate 1, as in this slide. And as soon as that writer is inside gate 1, the readers and writers are blocked on gate 1. So as soon as that writer's in there, nobody can get into the first gate. And furthermore, if a writer tries to enter through gate 2, what happens? He is blocked until the number of readers drops to 0. So this next slide shows that the number of readers inside gate 1 will eventually drop to 0, because eventually they will be finished reading and no readers or writers can get inside gate 1. Once that happens, the writer can enter gate 2. And when he enters gate 2, the readers and writers are still blocked on gate 1. So the writer only has access to do the writing of the database when nobody is inside gate 1, neither readers or another writer. And when the writer exits, then the system returns to its initial state. So that's the Tarekhoff algorithm. Now, interesting note, I have not been able to locate a reference to, I only just have a brief mention of the Tarekhoff algorithm, and I haven't been able to locate a formal reference to the originator of this algorithm. I just gleaned this from the documentation in C++17. So if anybody can send that reference to me, I'd appreciate it. All right, so now here's the code. Now understanding the Tarekhoff algorithm, I think this code is fairly easy to follow. And remember, start read is like is our terminology for the shared unlock. So now notice that inside, so this is class read-write monitor, and the attributes that we have a mutex, our usual mutex for mutual exclusion of the methods inside the monitor, and so we're going to call that RW mutex for read-write mutex. And here's our two condition variables, one named gate 1 and another one named gate 2. And as we indicated, there's an int readers that's initialized to 0 that counts how many readers are inside gate 1. And then we also have a Boolean, which is writer, which is initialized to false, because initially there's no readers inside and there's no writers inside either, so the writer is equal to false. So now let's take a look at start read. Remember the rules for start read? Okay, so what happens is we set up our unique lock, pass it the template parameter mutex, type mutex, and we set up our guard. This is using that usual RAII coding pattern for C++17. And our guard gives the mutex, our RW mutex. And now what do we have to, how do we get blocked trying to get in at the beginning? Well, if there's a writer, if writer is true, we can't get in, so we have to wait until not writer. So we're using our usual functional programming. We're passing a lambda expression for the function, and that function is just a one-liner that returns not writer. So that's very easy to understand. And then once we and by the way, we're doing start read. So once a reader gets in, we do readers plus plus, and so we're counting how many readers are inside gate 1. And then our end read. How do we do our end read? Well, again, we use our same RW mutex to guarantee our mutual exclusion using the RAII coding pattern. And since a reader is going to be leaving, we do readers minus minus. But now what happens is the last reader to exit the room, we have to, if there is a writer in the room, we need to notify that writer. We need to signal that writer so that he can enter gate 2. So we say if writer, so if there is a writer in the room, and readers equals 0. So if the last reader to exit, then we'll signal, if there's a writer in the room, we'll signal that, and so we'll do gate 2 dot notify 1. Okay, so that's the code for end read. All right, so now let's go to and see how the start write and end write works. So this next figure shows the logic for start write and end write. So let's take a look at start write. So now start write, this is when so what does a writer have to do to start write? Well, he has to get into the writer has to get into the first room, and then he has to get into the second room. So how does he get into the first room? So again, we have our RW mutex to guarantee mutual exclusion. And notice that we're not using a shared mutex now. So what do? We do gate 1. A writer has to do gate 1.wait. And what does he have to wait on? He has to wait until there is no writer in either gate 1 or gate 2. Otherwise, if there's a bunch of readers in there, as long as there's no writer, he can go in there and mix in with the readers. Once he gets in, he sets writer gets true. So now everyone else knows that there is a writer in the system. And then what does he have to do? He has to do gate2.wait. And what does he wait on? He waits until readers equals 0. So isn't that easy and simple to understand and read? I think this is a great algorithm. So this is gate2.wait, and then after he waits on gate 2, then he will get in through gate 2 and be able to start writing. So that's how a writer does start write. And now what happens when a writer ends, when he does end write? Well, here again we have our RW mutex to guarantee mutual exclusion. And our writer sets readers to 0. So he does readers gets 0. Writer gets false because he's going to be leaving. So he's setting up the initial state then. He's setting up the state to be the same as it is in the initial one. And then he does gate1.notify all. So all of the ones who are waiting on gate 1 have been notified that they can get in, have been notified that they can get in. So they'll get in some random order, and a bunch of readers can get in, and one writer can get in, and then the whole process will start all over after the writer has updated the database. And then this next slide shows the read-write database, and we have set up a little local monitor, RW monitor of type capital R, capital W monitor. So that's our local read-write monitor, and here's we have this is the same code basically from here on out as we had with the previous solution in ReadersWriterC. We have we initialize an int myData to be equal to 5, and then as usual the readers read it and the writer increments it by 5. And so this code all is very similar to what we had before in ReadersWriterC, and I think it's pretty straightforward to understand. And furthermore, the main program and the reader run and the writer run are identical, so I'm just not going to show that here. Okay, so that's ReadersWriterB, which shows the specific implementation of the the solution to the ReadersWriters program without using the shared mutex. But this is actually what goes on behind the scenes. This is the code that actually runs behind the scenes in C++ 17. And now the next project that we're going to look at is ReadersWriterC. And ReadersWriterC is an optimized version of ReadersWritersB. And this is the actual code. I gleaned this from the reference implementation for shared mutex in C++ 17 documentation. And now these optimization techniques are beyond the scope of this course. And if you're taking this class with me this semester, I would not expect you to know any of this stuff on ReadersWriterC. But it's so interesting, and especially if you've had computer systems and you know how to bit twiddle. This is very professional code. This is the way it's actually done. So what they do in the reference implementation is in place of an integer to keep track of the number of readers and a Boolean to keep track of whether a writer is in the system or not, there is a single unsigned integer named state. And you really kind of have to know your Boolean operations to understand this code. The first bit of state is 1 if writer is true and 0 otherwise, and then the remaining bits are the count of the number of readers. And I have an 8-bit example here. Of course, in practice there'd be a 32 or 64-bit unsigned integer. probably these days more likely a 64-bit, but this really small 8-bit example, if the state is 00000110, then that, because the first bit is 0, that means there's no readers, and because 00000110 is equivalent to an unsigned an unsigned integer value of 6, that means that there are 6 readers and no writer. And as another example, the second example, we have the first bit is 1, and so that means that there is 1 writer in the system, and because 00000111 is equal to 7 decimal, there are 7 readers, so 7 readers and 1 writer. So that first bit is used to indicate whether there is a writer in the system or not, and then the remaining bits, the magnitude of the remaining bits, are an unsigned integer that is an actual count of how many readers are in the system. And then how do we extract the information from that integer? Well, we use this idea of a mask. So we have these 2 masks, and by the way, I have renamed this from the reference implementation just to make it easier to understand and to put it in the same terminology that we've been using in our textbook. But anyway, with the reader mask, the first bit is 1 and the remaining bits are 0, and the writer mask, with the writer mask, the first bit is 0 and the remaining bits are 1. So I've named this the reader mask and the writer mask. And now this next slide shows some code snippets in the optimized version of the Reader's Writer's problem, and the expression and its corresponding meaning. So now the first expression is state and writer mask. Now remember that the single ampersand operator in C++ is bitwise and. And so what we're doing is we're taking that state, which is that unsigned integer, and we are bitwise anding it with the writer mask. Now what was the writer mask? The writer mask had a 1 for the first bit and a 0 for all the other bits. So that means that what this does is this duplicates the first bit and it makes all the remaining bits 0. Now recall that in C and in C++, any integer value that is all zeros, that is, in other words, the integer 0 is false, and anything that is not all zeros is interpreted as true. So this is actually interpreted as a Boolean value, and it will be true if and only if a writer is inside gate 1 or gate 2, because if a writer is in there, the first bit will be 1 and the remaining bits will be 0, and that is not 0, and so that is interpreted as true. And otherwise, if the writer is not in there, then the value of that expression will be all zeros, and that will be interpreted as false. So that expression is true if and only if a writer is inside gate 1 or gate 2. And similarly for the number of readers, if you do the state and the reader mask, that zeroes out the first bit and leaves the remaining bits unchanged, and so those remaining bits are literally a count of the number of readers inside gate 1. Now the next 2 expressions are really slick because this code is designed to work even if it is designed to work so that you cannot overflow the integer value of the count of the number of readers, because after all, the default in C and C++ when you do integer arithmetic is if you add 1 to the maximum integer value that you get, then there's no exception handling for that. The integer arithmetic just continues to loop around, and you get an overflow, but the answer is incorrect. So what this code does is this code actually has an additional requirement that you cannot have so many readers inside gate 1 that you overflow the integer count of the number of readers. And so look at this next expression. It's state and reader mask. And if that equals the reader's mask, that is true if and only if the number of readers inside gate 1 is the maximum we can count. And so if a reader tries to get into through gate 1, but the number of readers inside gate 1 is already at the maximum number we can count, we're going to block that reader. So this is an additional constraint that you can't have more readers inside gate 1 than you can count with this finite precision integer value. And so that expression, state and reader mass equals reader mass, that's true if and only if the number of readers inside gate 1 is the maximum we can count. And then if you subtract 1 from that, that's 1 less than the maximum that we can count. So if that value, if readers equals reader mass minus 1, that means that we can allow a reader to get inside gate 1 because we can count 1 more. Now, the next 3 lines of code show how to add 1 to the number of readers. Basically, what you have to do is extract the number of readers from the state variable, and so we have a little local variable named readers, which is an unsigned integer, and that gets state and reader mass, which is the number of readers, and adds 1 to it. But now what we have to do is we have to put that back into the state variable without changing whether or not a writer is inside. So the second line of code, state and gets writer mask, extracts the first bit from the state and makes the remaining bits all zeros. And then the third line, state or gets readers. Again, this is bitwise or. So state or gets the number of readers, then restores the state variable to have the same first bit where with the number of readers incremented by 1. So it takes 3 lines of code to add 1 to the number of readers and to modify the state accordingly. And then the last little fragment of code, snippet, is how to change the state to indicate that there is a writer inside without changing the number of readers. And that's a very simple or gets. It's a bitwise or. So this is equivalent to state gets state or writer mask. So that sets the state to specify that a writer is inside. And now there is one more item that is optimized, and that is that the implementation of this programs the spurious wake-up loop explicitly without using the predicate parameter in the wait function. So this is super optimized. We don't even rely on the built-in spurious wake-up loop. We program that explicitly. And an example of this in the code, in the optimization code, is whereas before when we said gate1.wait guard and we waited until until there was not a writer inside, well, that is coded explicitly by saying while state and writer mask, which is here again is interpreted as true if and only if a writer is inside. We actually explicitly code that as a while statement, and that's while state and writer mask is true, then gate1.wait guard. And so that we don't even rely on the code that does that automatically for us, but instead we use this optimized version. And now with all of that in mind, here is the code for the this is the actual reference implementation, again with my naming of these various variables and using start read and start write and end read and end write and so on, as well as some of the masks and things like that. I've changed the nomenclature, but basically it is the exact algorithm in the reference implementation. So here again we have RW mutex is our mutex for mutual exclusion. We have the 2 condition variables, gate 1 and gate 2. And here is that unsigned state, unsigned integer, state gets 0. And this next line that defines a writer mask is, you can look up the C++ stuff with, it's platform independent, it's system independent, so that it will work on any platform, whether it's 32 or 64-bit. You can look up the C++ details for how that works for the writer mask. And then the reader mask is bitwise the bitwise not inverse operation, the not operator on the writer mask. So the writer mask is set to be, first bit is 1 and the remaining bits are 0. And it does that with the left shift appropriate number of times, shifting in zeros from the right. And then the writer mask is just the bitwise inverse of the, the reader mask is just the bitwise inverse of the writer mask. And so here's our start read. We have our usual read write mutex to using the RAII. And then now here's all those expressions that we saw. Remember we said that there was so while state and writer mask, so that's while there, and so this is our explicit programming of the spurious wake-up loop. While state and writer mask or state and reader mask equals reader mask. So remember, we have to wait until that's. While that is true, we have to wait. We have this local. We have to add 1 to the number of readers, and so there's those 3 lines of code that adds 1 to the number of readers without changing the whether or not a writer is inside. And then here is the end read code for end read, and we have our usual RW mutex for end read, and now we have this little local variable readers because we have to subtract 1 from the number of readers, and so we have to use these 3 lines of code to, subtract 1 from the readers without changing the first bit of the writer mask. And then the if statement in our original ReadersWriterC said if writer and readers equals 0, so that and is coded as a nested if, but it's the same logic. And now we have another little else that is not necessary in our previous implementation, because recall that if there are readers blocked on gate 1 because we have the maximum number that we can count, we have to make sure that if a reader leaves and now there's room for another reader in, because we have the ability to count that number, so we have to unblock them by doing that signal in the else part of this code. And then actually that's the most complicated part. I think the rest, the start write and the end write, is not that difficult. Again, with the start write, we have we program the spurious wake-up loops explicitly with the while, and we have to do it. So that's just a straightforward translation of ReadersWriterC for the start write, and the same with end write. So I could give you the demo of the code for this, but it would look identical to the demo of the code for all the other ReadersWriterC problems with this setup with this database, so I don't think we'll take the time to do that. And now the last code that we're going to look at is just a simple demo that if you code up the solution to the ReadersWriterC problem with the Hoare semantics, but you actually use Mesa semantics with C++, that algorithm doesn't work. In fact, it will deadlock, and this is a demo of that. So the ReadersWriterC is algorithm 7.4, which assumes Hoare semantics, and I've coded this up in C++ 17. Actually, in C++ 17, you cannot query the state of the condition variable Q, so you can't test it directly to see if it's empty or not. So the way around that is to maintain a count of the blocked processes for that purpose. So there is no empty method in C++ 17. So here's the code for the ReadersWriterC, and so here is the notice that it's the same read write mutex and OK to read, and here now the condition variables are called OK to read and OK to write instead of gate 1 and gate 2, and we had that integer variables to keep track of the number of readers and writers. And then here's, I added this blocked on OK to read, an integer initialized to 0, and blocked on OK to write, also an integer initialized to 0, so we can tell how many, we can test whether or not a reader or a writer is blocked. And then here's the code for it. For that, I don't think I'll go through this line by line because it's not that. If you want to take a look at this code and verify that it's a translation of that Hoare semantics, you can do that. I don't think we'll take the time to do that here. So here's the start read and end read, and here is the start write and end write. And then we will conclude with a demo of this ReadersWriterC to show that it will deadlock, and that so the semantics makes a difference. You know, whether it's Mesa semantics or horse semantics. A solution for one might not work for the other, and vice versa. So let's do that little demo, and then we'll wrap up. Okay, so here's our demo. First of all, let's do a quick little demo to show that ReadersWriterC actually works. Here's the code that we did the walkthrough on. You see all this optimized stuff with the condition variables, gate 1 and gate 2, and we have this state that's initialized to 0. Here's our start read, here's our end read, here's our start write, here's our end write that we did, that we showed on the slides. And here is the database, which is similar to the database that we had done before. And like I mentioned on the slides there, here's the reader run and the writer run, and they are identical to what we did before. So this is ReadersWriterC, so let's run this and show that this works. And boom, there it is. We see that writer 0 is about to write, writer 0 wrote 10, then reader 1 is about to read, reader 0 is about to read, reader 2 is about to read, and then they all three of them read 10. And then a writer got in there, was about to write, and he changed the 10 to 15, and some readers read, and etc., etc. So that worked good. Okay, so now let's take a look at ReadersWriterC, and we'll show that deadlocks. So here's ReadersWriterC, here's the code. We just did this briefly, we didn't do this line by line, but anyway, here's the code for the horse solution to the readers writers problem, but unfortunately we are using Mesa semantics with C++, and here's the database, and here's the reader run and the writer run, and so on. So that's the same. So let's change this to ReadersWriterC. And this time when we run it, I predict deadlock. And boom, sure enough, writer 1 is about to write, reader 1 is about to read, reader 1 read 5, writer 1 wrote 10, and we're deadlocked here. Let's see if we get a different sequence for if we run it again. We'll interpose here and kill that process, and we'll do it one more time, and we'll see if we get a slightly different output. I think we did get a slightly different output, but still it deadlocked. So let's stop and rerun it again one more time, and ooh, it deadlocked really quickly this time. So anyway, that's the demo that ReadersWriterC deadlocks. All right, good deal. End of demo.
I think what I'll do is I think I'm just going to sign off. I don't know that there's any benefit to reviewing online. So, hasta la vista, baby.